The body of a human being, when seen under the lens of a microscope, slowly gave up its ancient secrets to the curious minds of science. Welcome to UncoverTime, where today we witness how brilliant minds across Europe uncovered the structures and functions of our body in an age before machines and modern medicine. In 1651, Jean Pecquet of Paris traced the course of the lacteal vessels. Then in 1653, Olof Rudbeck in Sweden discovered, and Thomas Bartholin in Denmark described, the lymphatic system, and in 1664 Swammerdam found the tiny valves within it. That same year, Regnier de Graaf showed how the pancreas and bile worked deep inside the body, while his friend Nicholas Steno found the hidden ducts of the parotid gland and later the tear ducts of the eye. Graaf also studied the testicles and ovaries, and in 1672 he described small sacs carrying eggs, now called Graafian follicles, while Bartholin noted two oval glands near the vagina, and Cowper in 1702 discovered the urethral glands that still bear his name. Franciscus Sylvius, teacher of Graaf, Swammerdam, Steno, and Willis, gave his name to a fold in the brain, and Thomas Willis, in 1664, published the most detailed map of the nervous system so far, describing the circle of arteries now called the Circle of Willis. The most brilliant anatomist of that age was Marcello Malpighi, born near Bologna in 1628, who studied medicine, taught in Pisa and Messina, then returned to Bologna to spend 25 years teaching and discovering the deep structures of life. He first focused on plants and silkworms under a microscope, almost losing his eyesight in the process. Yet he said the beauty of nature he saw gave him a joy too great for words. In 1661, while observing the lungs of a frog, Malpighi saw blood move from arteries to veins through tiny connecting tubes, which he called capillaries, a discovery that finally proved how the blood circulates through the body. He found that these thin vessels existed everywhere. Blood changed its path, making the circulatory system complete in human understanding for the first time in history. But Malpighi's discoveries did not stop there. He was the first to show that the tongue's papillae were used for tasting, and the first to describe red blood cells, although he thought they were fat droplets. He gave accurate reports on how nerves and blood vessels formed in unborn babies, and he studied the structures of the brain, spine, and lungs in a way that helped future scientists understand how the body breathes. His name became part of the body itself, the Malpighian tufts in the kidneys, the Malpighian layer in the skin, and the Malpighian bodies of the spleen, as if he had written his legacy into our flesh. Though his ideas were challenged by others, Malpighi defended himself with energy, and in the end he sent his discoveries to the Royal Society in London, who published his life's work as a form of scientific autobiography. In 1691, he was honored with a position as physician to Pope Innocent XIII, but only 3 years later he died suddenly from a stroke, leaving behind a body of work that founded the science of histology, the study of tissues. As anatomists studied deeper, they noticed surprising similarities between the bodies of humans and animals, sparking debates about the natural order of creation. In 1699, Edward Tyson published a study on the orangutan, calling it a man of the woods, and describing its physical features in comparison with those of humans, in an effort to better understand the diversity of creatures. Even as some ideas stirred controversy, most scientists of the time stayed cautious and respectful of religious teachings, avoiding conclusions that went beyond the evidence. As the study of structure advanced, so too did the study of function. Physiology began to replace mystery with reason, and the old belief that breathing cooled the body gave way to new ideas. Robert Hooke proved that breathing was not about cooling, but about exposing the blood to air, and Richard Lower showed in 1669 that venous blood could turn red again when exposed to fresh air. Lower guessed that something in the air, a nitrous spirit, was responsible for this change, and his friend John Mayow took this idea further by calling them nitro-aerial particles. Mayao believed these tiny particles entered the blood through the lungs and caused the heat of life, especially after exercise, when more of them were absorbed due to heavier breathing. He thought these particles were the key to life in both plants and animals, connecting respiration to combustion and making breath itself a source of inner fire. As these ideas spread, a great debate began. Was life just a machine made of chemicals and movements? Or was there something deeper, something living within that could not be measured? Some, like Borelli, tried to explain every function of the body using mechanics and mathematics, reducing muscle movement to pulleys and levers. Steno, a Catholic scientist, dismissed vague ideas like animal spirits and supported the view that the body was a machine controlled by known forces of physics. Descartes had imagined the body as a machine long before, and now that idea seemed confirmed by experiment after experiment, turning even digestion and motion into mechanical events. But others resisted this cold explanation of life. Francis Glisson said that living tissues had a natural irritability that dead matter did not, a quality that hinted at something beyond physics. Like Newton, who believed that the universe could only have begun by the will of a creator, Borelli also believed that the body, with all its complexity, must be guided from within by a soul created by God. Claude Perrault reflected that even the heartbeat, which we now call automatic, may once have been an act of will, shaped into habit by the soul's continuous command, showing how divine design allows body and spirit to work together. Georg Stahl declared in 1702 that every process in a living being, from breath to digestion, was not merely chemistry, but the work of a soul placed in the body by God, a soul that gives life, purpose, and harmony to all organs. For nearly 2 centuries, this belief in a vital force guided science, even as mechanical explanations grew stronger, until it was challenged again by new discoveries in the 19th century. Yet even today, some still ask whether life is more than motion, whether some part of the body carries a mystery no tool can measure. Much of the early progress in biology came from the practical needs of medicine, for health was the highest goal, and people turned to anything that promised a cure, from prayers and stars to science and kings. One doctor was said to pray so often before treating his patients that his knees became hardened, while royal surgeons recommended bleeding patients only when the moon was in a certain phase. Quack healers took advantage of desperation. Defoe joked that the money paid to them could have cleared England's national debt, and Charles II once touched 8,500 people in a single year, believing it would cure their illness. But William III refused such rituals, calling them superstitions and giving money instead, though many called him an unbeliever for it. Diseases still spread widely, helped by poor hygiene and crowded cities. Syphilis infected actors and soldiers, smallpox killed royals, and the plague returned again and again. Malaria was so common that Thomas Willis said nearly all of England was turned into a hospital in 1657, while plague killed tens of thousands in London, Vienna, and Prague within just a few years. With the rise of new industries came new diseases. Painters were poisoned by chemicals, miners caught tuberculosis, potters got dizzy from fumes, and printers lost their sight, all detailed in Ramazzini's classic 1700 book on workers' illnesses. Yet the thirst for profit sometimes held medicine back. Doctors who discovered successful cures often refused to share them with others. Thankfully, scientists in the Royal Society promoted cooperation and open learning, and schools like those in Leiden, Bologna, and Montpellier set high standards for medical education. Medical thinkers split into 2 camps: those who saw disease as a mechanical breakdown and those who saw it as a chemical imbalance, especially of the body's fluids or humors. Sylvius, one of the leading teachers, believed that many illnesses came from excess acidity and used drugs to balance the body. He was the first to connect lung tubercles with tuberculosis. One of the most visionary figures of the age was Athanasius Kircher, a Jesuit genius who used a microscope to find tiny creatures in the blood of plague victims and in rotting matter. He published his results in 1658, arguing that these invisible worms were the cause of disease, an idea that laid the foundation for the germ theory centuries ahead of its time. But even with all this knowledge, medicine moved slowly. Those who researched disease were often far from those who treated the sick, and strange folk cures still appeared. A woman once tried to poison her husband with a boiled toad, but instead cured him of dropsy, and so the treatment became famous. New plants and remedies entered the pharmacies: tea, peppermint, cascara, and ipecacuanha, and Dutch doctors began prescribing tea as a universal medicine. The greatest teachers of medicine were two Dutchmen, Sylvius and Boerhaave of Leiden, and Boerhaave especially helped transform medical education by training students directly at patients' bedsides. His book spread across Europe and even into China, and his teachings raised the respect for doctors everywhere. In England, the most famous physician was Thomas Sydenham, who believed that disease was nature's attempt to heal the body, and the doctor's job was to help or step aside. He said fever was not the illness itself, but the body's way of defending against it, and he admired Hippocrates for treating with minimal medicine and maximum observation. Sydenham believed every disease had many forms, so he carefully studied each patient and gave names to illnesses like scarlet fever, which he separated from measles. He earned the name the English Hippocrates for his careful records, thoughtful diagnosis, and respect for nature's own healing power. Surgery, meanwhile, fought to be accepted as a noble art, standing between the scorn of physicians and the rivalry of barbers, who still pulled teeth and made small cuts. When the surgeon Felix cured Louis XIV's painful fistula in 1686, he was richly rewarded with gold, land, and nobility, helping surgeons rise in French society. Surgery was finally declared a liberal art in France in 1699, and Voltaire later said that France had become the greatest nation in surgical skill. England also made advances. In 1662, Major performed the first intravenous injection, and in 1665, Richard Lower successfully transfused blood between animals. But pain relief was still crude. When Pepys had a bladder operation, he received no anesthesia, just a simple drink for comfort, and he survived only by luck. Doctors were still mocked in plays and jokes, criticized for their fees, strange clothing, and sometimes fatal mistakes. Yet behind the laughter, science was moving forward. The 1600s gave medicine new tools, new knowledge, and new hope. International collaboration increased, and the foundations for modern healthcare began to take shape. Governments began to act. In Rome, during the plague of 1656, health officials ordered clean streets, inspected water supplies, and even required certificates of health for travelers. As wealth grew, people built stronger houses, kept rats out, and drank safer water. Step by step, the body and the world around it were being cleaned and civilized. Today, the capillaries Malpighi saw under his microscope are now studied through digital imaging as doctors scan entire organs without ever making a cut. The nitro-aerial particles, imagined by Mayau, are now known as oxygen molecules, measured precisely in every hospital, in every breath. From crude surgeries to robotic operations, from boiling toads to targeted therapy, the human desire to heal has never stopped. And it all began with the microscope and those who believed that creation could be understood. Thank you for watching UncoverTime. Like, share, and subscribe for more journeys through history.